Hello, I am Devesh Kumar Srivastava and I am going to present my paper in International Conference on Recent Trends in Machine Learning IoT Smart City and Application at Hyderabad. My topic is prediction of osteosarcoma using machine learning technique. This is my abstract part of my paper. Osteosarcoma is the name given to the most common bone malignancy which occurs in individuals of 5 to 25 years of age. And this is study focus on finding out a prediction algorithm by comparing widely used algorithm on both feature and image dataset. The aim is to find an algorithm which commendable accuracy which can be used in clinical setting. This work is basically done in two halves, one on the feature dataset and second on the image dataset. The algorithm used for the feature dataset are XRT classifier, convolutional neural network, XGBoost classifier, and DenseNet classifier. The concatenation of viable and neoplastic tumor gave the highest training accuracy of 96.22%, followed by the group of non-tumor versus viable, which gave the training accuracy of 94.56% compared to the others, as discussed in our later part. For the image dataset, convolutional neural network is used to predict osteosarcoma. We managed to implement the model by utilizing trainable 2.5 million parameters of convolutional neural network, which indicate that the model works on less complexity. Introduction. While bone tumor is responsible for approximately 5 to 10% of new cancer cases in early stage, osteosarcoma is the most familiar form of bone tumor and it has a 5-year survival rate of about 60% as per the reference paper 1. The malignant is seen to be developed in individuals of 5 to 25 years of age. There are age peaks of occurrence among the patient, which a peak age of youngsters may need age 10 and teenagers at age 10-20. Osteosarcoma is a form of mesenchymal tumor which often metastasizes to the lung and peripheral bone. Therefore, metastatic ability is the key element in figuring out the analysis and diagnosis of osteosarcoma. The symptom and sign of the osteosarcoma typically start with a moderate bone pain, which is generally localized, redness, and heat on the place of the tumor. This is my literature survey part, and I would like to skip because of the time limitation. So I have surveyed some few research papers, which is mentioned in our presentation, as you are seeing in the screen. This is my proposed work and how we can use the concept of the methodology in our research work. You can see here. The dataset used in the retrieve from the research of Rajalam et al. This is the reference from where we can use the dataset. The dataset contains both hematoxylin and eosine sustained osteosarcoma histology pictures. The pictures are labeled as non-tumor, viable tumor, and necrosis in keeping with the vein cancers kind in every photograph. Sample pictures are shown in the figure. As you can see that in the image data set 1, 2, and 3. This is the picture. This is the sample data set. The data set includes 1,144 images of length 1024 cross 1024 at 10x precision with the subsequent distribution. Like 47% are non-tumor features, 23% are narrow tumors, and 30% are tumor files. So before going to use the image dataset, we have to pre-process. So the feature dataset of 1,244 rows with 69 columns is split into training and testing with the ratio of 80% and 20% respectively. The dataset is unbalanced and so far an unbiased and stable results. We have balanced the dataset with augmented images in all three data classes. The updated dataset has 1,740 images in training dataset. The dataset is split up into the training and testing with a ratio of 70% and 30% respectively. And for deep learning model, the image dataset is randomly rotated and normalized. For all retained models, the width and height are reduced to the required size needed for the classification of input images and then normalized with the mean and standard deviation. So in this way, we can pre-process our dataset before implementing using the convolutional neural network. And this is our proposed model. We started with applying different machine learning algorithm on the feature datasets, namely extra-tree classifier, convolutional neural network, XGBoost classifier, and DenseNet classifier. Convolutional neural network is chosen for the application of image dataset. The dataset resulted in overfitting when it is applied to the high complexity and run for epochs greater than 40. The use of 2.5 million parameter offered an insight that the dataset would work on lesser complexity and still be able to offer good results. So when we implemented the concept of the extra tree classifier, then extra tree classifier gave the best results in terms of validation accuracy. Extra tree classifier is implemented and tested with the various number of decision tree presented in the forest with both 0.9 threshold and 0.99 threshold values of the dataset. The classifier gave its best results, that is 82.7 when implemented with 500 decision tree with a 0.9 threshold dataset values. This is the architecture of the convolutional neural network. You can see here there are so many layers: input layer, convolutional layer, pooling layer, convolutional layer, pooling layer, again convolutional layer, then again pooling layer, and all this is the fully connected layer, and then we can receive the output layer. So in this way, we can put the images in the input layer, and that image has to be processed from the different layer, and finally we can get the output. So CNN model suggested in our application uses the RAM optimizer and categorical cross entropy for its hyperparameter. The architecture of the model comprises of 3 convolutional layers with the ReLU activation function and 2 max pooling layers, after which it is flattened and introduced to fully connected ReLU layers. A dropout of 0.5 is also introduced prior to the last layer, VGG16, for the classification of the following image dataset. We have used VGG16 as defined in our figure, as you can see earlier, as a feature extraction, and then embedded our own classifier for results. So we have to freeze the pertinent network for the node to behave as a feature extractor and then passed it through a classifier of 3 dense layer at ReLU layer. Batch normalization followed by a dropout of 0.5 with the output layer of log softmax as shown in the equation 1. We can further show in the next screenshot. You can show the equation 1 and equation 2. So you can see here, this is the equation 1 and this is the equation 2, right? So we have used NL loss function as shown in the equation 2 and RM optimizer with initial learning rate of 0.5. This is the algorithm. So first we have to input with the model, the data set, and the learning parameter, and our output with the accuracy and training loss of the model on the given data set, which is objective. So we have to propose step 1 for every epoch. We have to input the batch size in terms of image, train the model with the features of the data set. Then again, we have to forward propagation and computing the total loss via NL loss function. And again, we have to back propagation and update parameters by gradient descent values. Then we can record the total loss and accuracy for every epoch step 2 end. So we can use this equation, softmax activation function and NL loss function. By this equation, when we calculate the NL loss function in the total operation. So when we have to implement the XGBoost classifier, we can get the XGBoost tree as you are seeing in the screen. So actually XGBoost tree are listed below, which is used for better investigation as the better output. This is our results. The implementation of inception classifier led to training accuracy of 94.7% and testing accuracy of 92.1%. So you can see that DenseNet classifier gives the 91.76% with the testing accuracy of 92.1%, right? In addition to this, implementation of DenseNet classifier on the image dataset produced an accuracy of 91.676% on training datasets and 90.73% on the testing dataset, as you can see here. The concatenation if viable and necrotic tumor gave the highest training accuracy of 96.22%, followed by the group of non-tumor versus viable, which gave the training accuracy of 94.56%. So this result is shown in this table 1. So the limitation of this model is the consist of the shortage of evaluation of model from the pathologist, right? And it is recommended that model should be always used for the supervision of a pathologist. This method can capture the new cases in clinical practices. So therefore, the generalization of our model could have to be problematic to deal with issues. It might be useful to be adopted in medical facilities and clinical setting exercise performance, which you can see in our table, which is the form of the results. So we have to conclude that it is important to automate the prediction of cancer using computer-aided systems, since the human accuracy goes as high as 60% in case of osteosarcoma. The analysis is performed on 2 datasets, feature and image dataset. Therefore, our work not only focus on prediction using images, but it also focus on prediction of malignant cells using features of the cells, which include the count of red and blue bodies and thickness. As compared to the other studies done on the particular image dataset, we were able to RAM the accuracy using convolutional neural network and take it as high as 94.7%. The concatenation of dataset gave good result too. The accuracy for non-tumor versus viable tumor is the highest, that is 94.56% among all the research papers, which means that it can be used for the clinical settings. Thank you. This is my reference, which can be used to build this paper, and we can cite this reference in our research paper for the literature survey and for the data set also. So thank you very much. If you have any question or concern, then you can find out. Thank you very much. This is my contact email ID, devesh98@gmail.com. You can contact at this email ID also. And this is my brief introduction. Thank you. Thank you very much.